Hey friends, we got the long-awaited, the long-awaited magnetic scoop tutorial. So that's this giant part right here. The magnetic scoop has a lot of different uses. We're going to get into those today. Solar wind facing factor, ionization facing factor, the strength, winds, all this good stuff. What ionization does, that's a big question out there. Like, what on earth is that for? So the magnetic scoop, in a nutshell, is ye old ultimate particle collector. It's like an antimatter collector that does so much more. Incidentally, it functions a lot. Basically, it's using a magnetic field to trap particles, be they ionized or otherwise. Well, basically ionized particles. If the particles that it's trying to collect are not already ionized, well, then that's what that's for. So we're going to get into that, but before I do that, I wanted to touch on something really quick about the warp drives. In one of the earlier videos, you saw that there were some issues with two warp drives on the same vessel charging appropriately. Some mismatches in calculations. I don't know what was going on. Freethinker saw that. I was working on a fix, has partial fixed up in the beta version of Interstellar, so I'm not too concerned about that particular thing. It's actually kind of neat because if you have the Breaking Ground expansion there from for Kerbal, you get the robotic parts and the Cal 1000 controller unit, which is basically a little script box. You can assign values to it in the VAB or the spaceplane hangar, but in the editor, basically using action groups. You click a little button and then you click a part and select a value like something that you would normally select for an action group with a hotkey 1 through 10 or 1 through 0. Instead, you assign it here, and each little blue dot on the timeline, you can set how long it goes, and then each little blue dot there is a trigger for that particular action group. So what this does is it starts charging the top drive. It then immediately reduces exotic matter percentage 30 times at an increment of 5% each, so 150%. It reduces it from 200%, which is what it starts off over here. You hit charge and it starts off at 200%. It'll reduce it down to 50. And then this line down here has 10 increments of increased exotic matter percentage for the bottom drive, which puts it up to 50. So it puts it at 50 here, 50 here, the thing charges, boom. Now, if you hit activate warp drive in that scenario, it will use this, it'll dump that back down to 0, so you're not maintaining that anymore, but it won't touch this. It'll leave that in, so you'll be overworking your reactor, producing exotic particles that you're not actually using. So a second track editor, Warp Controller 2, what it does is it activates the top drive, clearing out its exotic matter, and then it stops charging the bottom drive, clearing out its exotic matter. Reset these scripts to use them again. And then basically, boom, you've got warp in just a couple steps. So let's jump into space real quick. Go ahead and set our orbit. Okay. Alrighty, so editing into space, we get an orbit of around 86 kilometers, 86.7 kilometers. That's pretty close to the planet. It's a pretty tight orbit, low Kerbal orbit. And what you're going to see here immediately is that you've got some movement here. It's like, oh, what stuff's going on? So let's face prograde. And I want you to keep an eye on our velocity right here. As we're in a perfectly circular orbit, we are not losing or gaining momentum. We are just right on the nose. Okay? Look right there. We are neither climbing nor descending. So we point in the direction of prograde at low orbit. Now I do have a dual technique magnetometer on here. Let's go ahead and whip that out so that we can compare some readings really quick before we start. Okay, our flux is 1.12 times e to the negative 6. It's pretty low. In general, that translates into no actual antimatter collection at this particular altitude. Actually, I'm sorry. We're not even collecting. Yeah, that actually translates into 0.0041 milligrams per hour. My mistake. That is actually enough to collect a tiny fraction of antimatter. Not much, but still a decent amount. Now, let's go ahead and turn that back off. So, if we look up here, our ionization facing factor is 0, so we are not actually facing the right direction. Most likely because we are on the side of the planet that has, the sun's pointed at us. So it's kind of stripping away any part of math, science, I don't know the full deal, but we're not going to get any ionization at this juncture until we open up this here collector and activate it. So, real quick, let me just kind of show you what's going to happen, because this is going to happen pretty quick, so I don't want you to miss it. As soon as we open this up, it's going to start working. So 86,744 is our periapsis, 86,752 is our apoapsis. Keep those numbers in mind. Alright, so we activate our collector, and it launches the shell off. It magically doesn't disintegrate everything, even though it should be a little bit of explosive force to make sure that those clear appropriately, or maybe it like blasts them off and then delays deployment. Anyway, you got your big antenna, big antenna, and we're immediately getting some things. Now take a look here, ionization factor 1. Okay, let's see. Yeah, facing factor is 1. So we are dead on prograde in orbit of the planet, which means this is the best orientation for ionization. Well, what does that mean? Atmospheric ion drag, okay? 2.7 times e to the negative 10 newtons per meter squared. So a very, like 0.0002 newtons per meter squared on a 40-kilometer area. That actually adds up. Okay, so orbital drag on vessel, solar wind force on vessel, all of these forces acting on your vessel, gas drag, solid vessel, all these factors are coming in at newtons per meter squared for every second that you're up here in space while collecting. Okay, and we haven't even looked at what we're collecting yet or how much we're collecting. Just to give you an idea, we are now looking at a periapsis that is at 86,730, 29. That was our apoapsis earlier, 28. Our periapsis former periapsis is now our apoapsis. We are losing orbit, okay, with this thing very quickly. So if we're not careful, we will deorbit while this thing is active. So what is it doing? What's it collecting for us? Is it collecting solar wind? Because that's what we thought it was for, right? Well, no, we're not collecting solar wind right now. We can't. We're in the magnetosphere of Kerbal. The magnetosphere of Kerbal is designed to block solar wind, so we're not going to get any at this juncture. Why did I switch those? Okay. So what are we getting? Are we collecting anything at this? Doesn't honestly look like we are, as far as things to collect. Alright, so really quick, one thing that we're going to need to do is match our drag so that we don't deorbit. So we're going to go ahead and turn on the dataless engine. Oh yeah, dataless. And let's see if we can limit that thrust pretty good. Let's see, half a kilonewton, it's 500 newtons, is probably still more than we need, but let's find out. Yep, definitely more than we need. So that's what that that's what that does. So let's reduce strength even more. Let's see, 0.5. barest hint of thrust. So we're pumping out 100 newtons. It's probably still going to be too much. Yeah, still too much. So, okay, you think, okay, well, maybe we're just going to have to do incremental burns. Well, not quite. Let's go ahead and turn this on. 2%. 2%. And we are losing, so we have to actually speed up now. Oh wow, that's actually extremely powerful. Let's turn that off. Alright, 4.7 kilonewtons was not enough to counter the drag produced by ionization at this altitude. So let's go ahead and work on raising that back up. 33 kilonewtons. Okay. A little more. 52 kilonewtons. Yeah, this might actually be I should have practiced this a couple times beforehand. Let's go ahead and just crank it up to 18%. And this will be the real challenge there, is figuring out how to use this thing without crashing. There we go. Now we're starting to really get some altitude. We can start slowing down. Alright, so let's get ourselves above the atmosphere again. And turn ionization back on. And see where we're at. And we're sinking again. A little bit of ionization is extremely powerful. There's a lot of drag going on here. So let's try full power. Alright, full power seems to do it. Barely. A little more ionization energy. 9%. Looks like we're getting a little bit of turbulence. Yeah, see, that's definitely not a good thing to do. Okay, so let's turn that off completely. Make sure that we can actually not die. Okay. So, basic thing there, the collector, or the scoop here, when you turn on ionization, it ionizes the particles in the upper atmosphere where the air is super thin, above the actual atmosphere, but there's still particles up there. And those particles can be ionized, strip away the electrons so it's got a charge, a positive charge, or zap it with too many electrons so it's got a negative charge. Either way, you ionize it and then scoop it up with the scoop. and this allows you to collect, particles from the interstellar medium, depending on what is actually present here. So as far as what is actually present here, let's see. Are we actually able to... I forgot if this thing actually told you exactly what it was collecting. I felt like that there was at one point a way to see that. Let's see, low density. Yeah, let's see, there was, the last time I used this thing, that actually told me how much in grams or milligrams I was actually collecting. Maybe I'm not seeing it. Or maybe I'm just not actually collecting anything at this point. Briefly turn this on. Ah, there we go. So, atmosphere hydrogen collected, 35 grams per hour. Atmosphere helium collected, 169 grams per hour is actually what we're getting. So at 1.3 ionization strength, which is enough to deorbit us when we're at this altitude, we are ionizing helium and hydrogen and collecting it. So that's going to get stored. Well, we're going to store the hydrogen in the antimatter reactor and the helium as well, but we're full up on these things. You can also collect things like nitrogen as part of the solar medium. Carbon dioxide is something you can collect. Helium-3, obviously, but we're not going to get any around Kerbal because of the aforementioned magnetic, shield around the planet that's scooping all that good stuff out. So let's take another look here. I believe this thing can also collect antimatter, and if that is the case, the best place for that to happen is going to be around 800 kilometers. So let's go ahead and take ourselves a little trip. Let's turn this off. Turn that off. And we're going to go ahead and activate the warp sequence. There we go. Now this craft is not nearly as boss as Yondu was in the challenge video that I made last night, or this morning rather, but it is good for science. It packs a lot of science, like actionable science, like things that we can go out and get some variables so we can know what's going on with the planet, as opposed to the pseudoscience where it's just like click on it and it gives you a science report. That's why I play in the sandbox, because for right now is because I want to be able to actually take readings that I can do something with. So that's what's in there, and there's a few other parts inside of here that you can't quite see because they're strapped to the walls, but we won't worry about that right now. What we're really doing is just trying to figure out how all of these parts work together. So we're almost fully charged, and instead of hitting activate warp drive, I'm actually going to hit this sequencer right here, which is going to allow us to do that. So let's reduce speed and then fire the warp drive, and then we will deactivate as normal right there. So 864, let's check our flux. Magnetometer says 4.5 times e to the negative 5, so that's a nice number. Antimatter collection translates into 0.16 milligrams per hour per standard size collector. So that's actually really decent for being around Kerbal, and you're getting every 10 hours, say, you're going to get a gram and milligram and a half of antimatter, which is when you're using it in the the really small range, it's a respectable amount. Anyway, we're going to turn that off to make sure that we are not collecting antimatter. We are actually using it. And then we are going to activate our magnetic scoop. Face prograde. Apparently prograde for us is in the opposite direction of travel. Yeah, our prograde's backwards. Let's see if that makes a difference. Activate the collector, and facing factor of 1.0, still valid. Solar wind facing factor 0, no solar wind at this point, so sun's on the other side of the planet. This is blocking solar wind, even though we're quite far out into the magnetosphere where ionized particles can exist. But nonetheless, we are going to turn this on, and currently it doesn't say we're collecting antimatter. We're still losing it quite rapidly. Now we are using an antimatter powered reactor, so that's going to kind of factor into that. So let's take a look here at the drag before we turn on the ionization. Let's see. Atmospheric helium, not bad. Hydrogen, helium. So this is a good spot actually, because there's quite a few different particles that we can collect up here. It tells you it in molar density, and also in kilograms here for the density of the actual gas, but in actual particles it tells you like neutral atmospheric helium 1.7 times e to the negative 10 moles per meter squared or cubed, I can't really tell. Anyway, let's see how much we can collect here at 1%. So we pop out 1% and we are collecting atmospheric hydrogen, 9 times e to the positive 7 grams per hour, 4 times e to the positive 7 grams per hour of atmospheric helium. Either way, it doesn't matter because we can't actually store any more hydrogen or helium, and we are not collecting helium-3 because it's just not present around Kerbal. Now, as far as antimatter, it does not appear that we are collecting antimatter still using this. Now, if we turn this all the way up, we are collecting atmospheric hydrogen at a rate that is absurd. That's 200,000 grams per hour. So 200 kilograms of hydrogen per hour right outside Kerbal, with this bad boy pumping out 1 gigawatt, or sucking at 1 gigawatts of power. 1 gigawatt of ionization energy, about 864,000 meters from the surface of Kerbal. Facing prograde, we are collecting kilograms of hydrogen. So you can use that to fuel your hydrogen-fueled vessels fairly quickly. It's absurd, really, how much you can do that. So that's, yeah, it's not that far out. All right, so that's what you can do with that. If we zoom, you can kind of see how much you got there. But as far as antimatter, we're not going to catch that here. All right, so let's disable the collector and let's take a look at what happens when we go into interstellar space when we're not using ionization, but rather just soaking up solar wind. Because so far we haven't collected any solar wind. We've only collected helium and hydrogen around, Kerbal, way up, where the atmosphere is so thin it's ridiculous. And honestly, what else can we possibly expect to find in that location other than trace particles of hydrogen and helium? All right, so let's reset that. reset that, and then start charging. This will take a moment, so I'll go ahead and time accelerate to speed that up. One more time acceleration. And 3, 2, 1, fire. Alright, so we're going to drift along. Make sure we get well outside the sphere of influence of Kerbal. That looks pretty good right there. Okay. All right, so just for the reference, we are actually going to point radial in as far as our target. We're going to point at the sun as opposed to pointing prograde. So completely different order of operations. We're well outside the sphere of influence here. Kerbal is 878,000 kilometers, so we increased our altitude by a factor of 1,000. It's kind of cool. Alright, so we are out in deep space. Deep space, okay? And if we take a look here, solar facing factor is what we're going to look at. So we activate the collector. Now we are pointed directly at the sun. In the gravity well of the sun, radial in is going to point you at the center of the sun, or the center of Kerbal. So that'll be a good reference there. So we are pointed directly at the thing. Okay, that gives us a solar wind facing factor of 1.0. Okay, force on the vessel out here in space is 2.3 newtons. Okay, it's pushing us. And the mass collected, just having this thing open, no ionization, 35 grams per hour. Okay, what we are collecting is just solar wind. That's it. It's just standard solar wind. Let me see if I can. Mass density. It's 10 times e to the negative 15 kilograms per meter cubed. Is what we've got there. Now notice out here in space, so that's what we're collecting. Mass collected 35 grams per hour. If we look over here, solar wind, that translates into 0.338 units is what we've got collected. Little tiny bit of solar wind so far. 270 some odd milligrams. We've got milligrams of solar wind. To do anything with this, we're gonna have to convert it using a refrigerator unit, which I have installed right here. And then you toggle the refinery window, and then you do the solar wind process. With the small amount that we have right now, less than 1 unit, we're not going to get much. So we're not even going to start that yet because it's not going to do anything. We won't even see what happens. But just to show you, 35 grams per hour. Now, altitude from the distance from the sun matters. The closer you are to the sun, the denser the solar wind is going to be, for obvious reasons, I hope. I mean, it's coming from the sun. It's going to be higher concentration at the source than, say, out by Elu. So, from Kerbal orbit, more or less, that region of space, that nice little Goldilocks zone where the planet exists at this altitude. I guess we're a little bit inside of it, but yeah, inside of that particular orbit. From this location, standard 35-36 grams per hour. Now, if we crank up the ionization, that doesn't move. 35 point, it doesn't budge. We're using all that power and nothing changes, which prompts a lot of people to believe that it doesn't work, because they probably test this magnetic scoop to collect solar wind in a position where they're going to be just collecting solar wind, and then they turn on ionization and they're like, it doesn't do anything. Well, no, it doesn't, because all of these solar wind particles that you are collecting are already ionized. every last one of them is an ionized particle. So ionizing them with the dish does nothing. If anything, it should repel them, but it doesn't. It doesn't. So it's for turning particles that are not ionized into ionized particles, is what it does. So when you're around a planet collecting, trace atmospheric particles, you ionize them to bring them into your collector. In the case of collecting solar wind, you simply point at the sun, and it's a very low power operation. Uh, 420 megawatts is what it requires, as opposed to the gigawatt that it requires for full power up here. Also, this won't do much to slow down your orbit because the drag is insignificant at this velocity. So you're not going to worry about crashing into the sun anytime soon. Okay. Now, here's the thing. I could show you this in two different ways. I could show you the standard way and then the fun way, but I'm just going to show you the fun way first. So one thing that really matters is distance to the sun. Another thing is velocity. If you're moving faster in a higher concentration of solar wind, you are going to collect more solar wind, per second or whatever. If you get closer to the star, and then you set up an orbit that has you, basically going down into the star, directly at it, so you can point your dish at the star as you descend on an orbit to collect more. You'll be moving faster and faster. You'll be collecting more and more. You could do that. You could also charge up ye ol' warp drive, and mind you, that collector is still on, and I shouldn't have done that because I shouldn't have done that. Doesn't actually have the strength to do that, so we'll try this again. And I do believe we are going to run into some problems. Okay, we have a tiny issue in that our vessel is definitely not going to do that. So let's try this again. Nope. Yell charging issues back? Okay, alright. Not enough power. Why not? Let's try a quick save, quick load real quick, see if that clears things up. Again, Freethinker said he's identified and he's working on that fix. Partially fixed already. I just haven't, I downloaded the update, I didn't install it yet. Just because I already had this thing built and just wanted to get through it. But we're gonna see if that fixed things. An editor. Warp window. See if we can do this really quick. There we go. Okay, we're back in business. Just had to reload. Silliness. It's okay though. Let's rearrange these. That there. That there. Close that one. Open that one. Alrighty. So, let's see if we can get away with opening this. Activate collector, and then fire the drive. Negative. The collector does not want to let me do that. Let's try something different. Okay, manually still works. And collector is still active for now. A little more thermal dissipation on this would probably help. I don't have nearly enough radiator action on this vessel. I really should crank that up. But we will see the results here in just a moment. As soon as that warp drive charges fully, we will take off. And what we're going to keep an eye on is solar wind mass collected, okay? Solar wind mass collected is what we're taking a look at right now. Here we go. Alright, we are off, traveling at the speed of light directly into the source. Solar wind mass collected is now in the kilogram range, 30 kilograms per hour, 33 kilograms. It increases, you know, the closer we get. So the longer we travel, the more we're going to get. But we are now, you know, getting, looks like 60 kilograms per hour. And if you look over here at solar wind, I mean, that just translates into your solar wind is filling up. You're just getting lots and lots and lots and lots and lots of solar wind as you warp towards the sun, which is the source of, you know, the solar wind, obviously. So let's take a look here. Oh yeah, look at that. Alright, so as we are creeping in here, super close, dangerously close to the sun, we are getting hundreds of kilograms per hour, and we're gonna get a little closer. I can see, yeah, that's close enough. Okay, that's close enough. Definitely close enough. Let's point directly at the middle of the star. Solar wind facing factor, close enough to 1. At this altitude, we are collecting, without any difficulty, 18,898 grams per hour. So just under 19 kilograms per hour of solar wind. We can't collect anymore because we've used it all. Okay? We are full on solar wind, and our antimatter reactor is going to disintegrate if we are not careful. So we're going to turn that off. And yeah, I didn't think about that, having an antimatter reactor that's close to the sun. Incidentally, as far as antimatter collected, about 17 or 18 milligrams per hour at this altitude, which is dangerously close to the sun. It's about 17 milligrams per hour. It's not the greatest, it's not the worst, it's definitely better than most other places, but it's not better than Joule, where you can get something like 60 milligrams per hour at the proper warp. This is absurd. I wouldn't expect anything to survive right here. You should be a little more out here. But at this point, as you saw earlier, you know, it's a 19 kilograms of solar wind. So you fill your solar wind collector up, you know, right away without any difficulty. Then you go to your refrigerator unit. You toggle your refinery window and you do solar wind process. You enable overflow, and the things that you're collecting, deuterium and liquid helium-3, as well as hydrogen, liquid helium. You can get carbon dioxide, nitrogen, and neon as well from this, from solar wind, because you're going to find all these in these orange little stars here. Also in percentage to what you would expect. So, you know, mostly it's going to be hydrogen popping out of there. Next is going to be helium. You're going to have some carbon and some oxygen and some nitrogen, and then neon, deuterium, and helium in super small quantities. But, you know, hydrogen, helium, carbon, oxygen, nitrogen is what you would expect from, that stars, and that's what you're getting out of the process. You were with the amount of solar wind that we had, we were processing it pretty quickly. We've collected it all, so let's go ahead and turn our collector. Let's turn our collector back on and see what this looks like, when we're collecting and processing at the same time. Let's turn our warp drive window off since we don't need that, and just put this right here. Put our magnetic scoop window right there. Also don't need that or that. Reactor control window, we're at about 3.5% use, so we can, for about 10 days. We have enough antimatter to do this for 10 days. Now, I did mention that we are able to collect antimatter here, so we might as well turn this on and refuel our antimatter reserves to there we go. Wow, that looks dangerous. That doesn't look happy at all. That looks hot. This could be bad. We might have to get out of here, but not yet. Not yet. All right, so we are producing, let's see, hydrogen 15 milligrams per hour, 200 milligrams per hour of helium, 200 milligrams per hour of deuterium, and 134 milligrams per hour of helium-3. That's really small amounts. It's super small amounts. But if you scale these up, bigger collector, more heat dissipation, bigger refrigerator unit, more storage, you'll get higher yield. But basic use of this thing is pointed at the source and try not to die. Again, ionization does not appear to do much. Yeah, it doesn't really make that much of a difference, except for how much power you're using, which would then rob other things of that power. But this close to the sun, you're going to be able to produce a decent amount of materials. If you want to get a higher yield, of course, just put a bigger refrigerator unit. This isn't the big one. Just put a bigger refrigerator unit, and you'll be able to process the solar wind pretty fast. Get a bigger collector. You'll be able to collect more solar wind at a time. And that's it. And then if you look here, 4.2 units per second is what we're getting just sitting here, as opposed to the absurd amounts we were getting when we were warping. Now, does this work if you're warping away from the sun? If you're warping away from the source? So let's take a look. Facing factor is currently 0, and we are not collecting any solar wind. I mean, it says we are, but the actual amount that we could possibly be collecting right now, nil. So we're not producing. Let's take a look here at the solar wind particle trap. Solar wind's not budging. We are not collecting solar wind at this time. So if you point away from the thing, you're not collecting the stuff. Alrighty, let's disable the collector, and let's compare what that looks like to one final thing. Let's open the editor and see if we are able to charge our warp drive. Yes, maybe, possibly. Yeah. Guess we'll find out. Let's put this right there. That right there. Go ahead and bring that back up. It's always useful to have that power management display handy. We haven't even gotten into using the Daedalus engine. I do apologize. I just have so much fun warping around that, sublight is just slow these days. Anyway, our drive is ready, so let's fire. we go. Works like a charm, see? Let's increase speed. And what we're going to do is see what this looks like around the outer solar system, and then I leave it to you, the viewer. Your challenge is to... Oh, that's not good. Well, that's not as bad as it could have been, I suppose. Those radiators, in fact, were designed as shock absorbers, and they did their job perfectly. You never... I mean, it's a bad idea to use an antimatter core as the backbone of your vessel, so I had those radiators strutted in there to kind of, you know, be a crush zone, and that's exactly what they did. So they performed their job admirably. I am super, super proud of my radiators for doing that. I am unfortunately a little miffed that that particular mishap happened in basically the Oort cloud or something, like beyond the lose orbit. No big deal though. Lugar and Billy Bobley know full well that we have a ship capable of reaching them in moments, so they'll just chill, look at the pretty lights, be thankful that they didn't disintegrate. I am going to try to turn around and see if it's possible to point and still complete our mission by gathering the last bit of data. Because science. Like, science rests for no one. Oh, this is bad. Look at all that. That's bad. Oh, no, stop. No. Point. 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 There we go. RCS. RCS. There we go. Okay. Alrighty. All safety's off. Activate. Oops. Go ahead and activate the backup generator so that the antimatter core doesn't have to work as hard. Alright, activate our collector. Silliness. Still producing power comfortably. Not a lot of thermal dissipation to be had in this instance, but we can still sit out here for about 12 days. So we're good. Okay, so at this altitude, what is this? 134,000 megameters. So like, what is that? A tera gigameter? Like 134,000. I don't know. We're up there. We're far away. We are super, super far away. And yeah, look at that. Now look, Dress is about to eclipse us. Planets will get in the way of solar wind and things like that, so I'm curious if this distance, how much of an effect Dress might have, considering it's tiny, but it potentially could cause you to see fluctuations in your readouts here. Anyway, at solar wind mass collected at this altitude is 0.338 grams per hour, so 1/3 of a gram of solar wind per hour. The force on the vessel is about 2/100ths of a newton. There's not much out here, guys. It's not completely empty though, as you can see, with one of these 40-kilometer effective range. Not like actually 40, but the field around it will collect 40 kilometers out. It's enough to scoop in 1/3 of a gram of material an hour. That's not insignificant. I mean, that tells you that space is not empty. If we learn anything else, it's not completely empty. There's stuff. It's just very thin. And if you collide with a piece of that stuff, even way out here, it could rip your entire vessel apart. So all of the vessels that I kind of designed in Kerbal Space Program would never actually survive space flight without some sort of plasma shielding, electromagnetic shielding, all sorts of different shieldings to prevent particles from colliding at light speed and disintegrating a vessel. Anyway, I hope that answers your basic questions there with the magnetic scoop. I leave it to you, the viewer, to figure out all the other cool stuff you can do with it. Take that sucker to Joule and see what happens when you turn it on out there. That's super fun. See what happens when you turn it on around Eve. See what you're able to collect there. And then take that sucker to an modded planet and see what turns up when you collect materials around those atmospheres. Anyway, stay tuned for the next video. Not sure what we're going to be, but it's going to be based on your recommendations and suggestions. And keep on playing. Have fun.